Okay, so most of you, I don't think, know much about this at all. And some of you have maybe heard some of this, so I apologize. But what I want to first try to explain to you is why there's a lot of interest in 2D materials in the popular press and even funding agencies. And I want to convince you it's not just about the materials. I mean, it's not like just some material you're modeling. There's something bigger going on here, and I want to explain what that is. So, and the best way I know to start is to discuss this very famous mathematical physics model called the Hofstadter butterfly. And simply what that is you have a square. This was in Douglas Hofstadter's thesis at the University of Oregon. And you simply have a square lattice, and you have, and you say, okay, I just model the electronic structure problem, the eigenvalue problem for Schrodinger's equation with a tight binding approximation, one orbital at each lattice point, and I put a magnetic field transverse to the lattice. That's added into the Hamiltonian by something called the Peierls substitution. So you have a well-defined Hamiltonian. You then say, okay, I want it to be, I want just some periodic structure in the y coordinate, which relates to the k, and then what I derive is this 1D problem in the x, in the x direction, and psi is the wave function value at lattice point L. B is a dimensionless flux. And so B is, so the flux, right, is magnetic field B. And the important thing is there's a length scale A. I want to argue about that in a bit. So BA squared is your flux, right? It's magnetic field times area. And then you normalize it by something called the magnetic flux quantum that appears in all the various quantum Hall and all these things. So this is a dimensionless quantity, and so then simply the issue is for each value, for a given value of B, I want to solve for the eigenvalue problem. So you plot the eigenvalues. So flux is B, and okay, so I sit here and this is just a plot. They're much more beautiful ones, and Hofstadter did it by very primitive plotting and computation. And what he observed was this sort of fractal behavior of the spectrum. And he writes, at first glance, the idea seems totally out of the range of possibility, since the rather generous lattice spacing of 2 angstrom demands a magnetic field of roughly 10 to the 9 G. So, okay, so now 10 to the 9 G is much bigger than anything that's been achieved on Earth. I went and checked. Being a mathematician, I know nothing about units. So Hofstadter was already aware enough to know that this phenomenal, this kind of very direct derivation from a physical argument gave something very interesting, but the parameters, the physical parameters, were outside the range of experimental validation. Okay, now...
Sorry, demands for what? It's not clear.
Say it again?
It demands for what?
Okay, so basically, this is a spectrum, eigenvalues of a Schrodinger equation. And basically, if this, and this is a dimensionless flux. And so A is a physical lattice spacing, say 2 angstroms, okay? And phi naught is just some fundamental unit. There's an electric charge there. Then you ask, what is the B that you can, the magnetic field that you can actually apply? And it turns out in the lab is all you can just probe a little teeny bit around 0. You can't really physically explore that spectrum. Okay, that's the thing. You really can just. Okay, so now the idea of several groups at the time was to look at putting okay, there already been a lot of hullabaloo about the exfoliation of graphene. We had a material of 1 atom thick that had all kind of amazing properties that I will mention a little bit about. And then people were starting to say, okay, what if I put one layer on another, but now I'm going to put it down on a slight angle. If you put it on a slight angle, you get what's called a Moire pattern. That means you have a larger length scale periodicity. It's just the Moire scale. And so you see here, red and blue are just hexagonal lattices, one twisted on another at a slight angle. And as you see, there's really another pattern here. There's another pattern, and and this is called the Moire cell, you might say, the Moire unit cell. We now have lattice Moire superlattice vectors instead of lattice vectors, and by the way, so all this, what the Moire is simply the beating, right, of the displacement with respect to the unit cell. Just like you have two sound waves, right, of very close frequency. You get fine scale oscillations, and you get a Moire envelope, the familiar beating. This is exactly the same thing going on here in terms of the displacement with respect to the underlying lattice. So now we have so the point is, though, it seems we have a larger unit cell. Now this unit cell is, and it depends on the angle. The smaller the angle is, the larger the unit cell. That's pretty easy to see. Is in their experiment, their unit cell was 15.5 nanometers compared to the unit cell of graphene. So you've really increased the size of the unit cell by a factor of 100, meaning the magnetic field you need is reduced by a factor of 100 squared, right? So, and now people really were able to observe the Hofstadter butterfly. And so to me, this is an amazing experiment. It says that now you have a new length scale. You have a new material with a superlattice, much larger than any known lattice previously, and in all those physical laws that because the theories all really work with dimensionless forms, and there's always some length scale in there. It's typically the lattice. Okay, and now we have a different length scale to put in all those theories, and there's a whole new set of physical phenomena that we can explore. So that really, to me, is kind of kicks off this whole new field. Okay, now, so I kind of came into this about maybe about 2014. At that point, we got funding to look at putting different layers on top of each other and twisting more in the materials genome kind of thing to see if you can design materials with given conductivity or whatever, optical this or that. So it was more of a materials design problem. So we got funding in this about 2014. One of the things that we developed kind of a new approach that I will talk a little bit about, based on kind of configuration, a new kind of trace, you might say. Okay, so the trace instead of, and I'll say a little more about that. And one of the things we've done a fair amount of work on is exploring the effect of the material relaxation on the electric structure. So this really combines mechanics and electronics very nicely. So this is just one layer twisted on another, but this is not the ground state mechanical structure because this has all these, because atoms, the carbon, say if it's carbon, they don't want to sit on top of each other. They like to form those what are called Burnell stacking, where the carbon sits in the middle, one layer sits in the middle of the carbon on the other. So to do that, you kind of form these regions of, let's say, ground state, and there's two forms of sitting there on where one layer has the atom sitting, and I'll talk about that. We developed a mathematical model for this, and recently we've also been able to give actually quite rigorous results on the effect on the band structure, the relaxation of the material. So this is, that was 2014, and so let's, so I want to set up what happened in 2018. So these are band structures. So band structures, I come from numerical analysis. It's just simply the dispersion of like a finite difference scheme, right? And now we have the same thing in sound, and you have the same thing in electronics. So you have, this is just these, so you have wave packets that travel. You can make up wave packets with group velocity given by the derivative of these bands. Okay, now, and you see, okay, so now these are energy levels. Now, zero refers to what's called neutrality. You just put, you put one carbon, one hexagonal graphene on another, and just in their, normal, without applying any fields, the ground state is zero. So you see, okay, at 0.5 degrees, but now something remarkable happens at near 1 degree. We now call it the magic angle, and this, and what we see is the bands become rather flat. So the fact that the band becomes flat, okay, and by the way, this is it redone with the relaxation. It's actually a much nicer view, because actually, if you look at it, in some sense, this is much nicer. Even though it's not a lattice anymore, it looks like you really have strong unit cells there, right? And whereas this looks kind of not so nice to me. But okay, the original work just did it for unrelaxed structures, and we had one of the early computations in our paper. So if you don't relax, you don't get actually a band gap, which is very important. So then if you actually do the relaxation, what you get is you have four of these flat bands. Now these are effectively flat. This energy scale is pretty extreme here. And so what that means is now these are dispersion relations for electrons. So flat band means the electron, or you might call it a quasi-particle. I never did take E&M over there. I just took mechanics. Okay. They use this word quasi-particle. Okay, so you make a wave packet, and these things are moving at this group velocity. And if the band is flat, the wave packet, the quasi-particle, is actually not moving. So that what that's meaning is that since they're not moving, they're actually interacting. The Coulomb interactions start to get significant, and they start to dominate the kinetic energy, which is the familiar Schrödinger, tight binding Schrödinger equation, really just captures the kinetic energy. So all these single particle models, which people use to compute band structure, that includes DFT and things like that. They don't include the Coulomb interactions, and that's your electronic correlations that lead to all these correlated phases. Now, so this was kind of a very nice paper, and I'll describe the result in in a bit, due to Bistwitch and McDonald, they actually did a very nice model that actually proves, or that shows that you can get flat bands at this magic angle, or actually they proved a zero group velocity, and but it took maybe 7 years for people to actually get the experiments done, and so people doubted it. Other people were doing things like checking even at a double E guy in Austin was checking. Maybe you know him. I forget his name. He was maybe what? No. He was checking maybe every like, I don't know, 0.1 degree, and he missed it, or he didn't have some refrigeration or whatever. So this Pablo Herrero at MIT, who probably had a gazillion times more funding and manpower, and a brilliant grad student who really was willing to work night and day. So they were able to show that they were able to demonstrate this called Modin, so these different phases, correlated phases, Mod insulator, superconductivity, and it's really, and this also shows you, and you see that it's actually the phenomena is very discrete-like, okay, and so the picture I like is looking at at an atom. You have your valence electrons, and now here, like I said, you have 4 bands. Each band can have 2 particles, right, with 2 different spins. So you really have like 8. You can accommodate 8 electrons in here. So it's sort of like this. It's sort of like taking this inner band and that middle band, and so really as you tune the voltages, etc., you can kind of go through there and see dramatic changes as you reach these integral kind of levels of filling of the of kind of filling of the Moiré. Remember, it's always the Moiré cell now. It's not the normal unit cell. Okay, so anyway, now something that's related that we actually had in our paper, Twistronics, that I never get tired of saying, kind of coined the field. It was in our paper, because we're now, in case you didn't know this, I've seen articles, we're in the age of Twistronics. It's true. It's actually Quanta or some other New York Times or somebody said that. Or maybe the NSF even said it. But okay, our paper coined this word Twistronics. Okay, so actually, I had the idea of writing this paper to get some of these math ideas in. Probably Tim came up with the word. But that's nice to coin the name of a field in your paper. Get you some nice citations. Because if you don't know anything, why not just cite the paper that started it all, supposedly, right? Okay, but one nice thing here, look at these, this is, forget this, look at this, this is our electron density, okay, it's kind of electron density at, say, charge neutrality, and as you look at 0.88, and you see at 1.11, which we did not know was the magic angle, you see that the density is most highly localized, okay, so I don't have a totally absolute mathematical proof of, my thinking, it just simply seems to me, it's like, okay, you take a Fourier transform of a constant and you get a delta function, right? Constant, flat, Fourier transform, delta. It seems like, okay, that's probably they're related, okay? Anyway, we had that sitting there in our work. Okay, so now what's been ignited now is everybody is now trying to create new platforms, they call it. That means, okay, you saw that you put one layer of graphene on another, and you got all this interesting stuff. Now you say, okay, let's now have one layer I'll twist in the middle and create a sandwich, or maybe you take, this is the ground state bilayer graphene, this Burnell stack, and you put one of those on another and twist, okay, and you, so then you have, and then here's another AB, so there, and here's now these TMDs. Now they're twisting those. These are nice because they're semiconductors. So, I mean, this is just, I haven't updated this. It's like, that's what experimentalists are doing. They're trying to create all these different platforms. Yeah, we started, the program manager said, oh, I don't want to hear the word graphene. I don't want to hear the word graphene. They've already funded it. And Richard, you told me, oh, Molly's dead. Remember you said that? I mean, you don't remember that. At Lake Arrowhead, I remember everything you say. We were talking at Lake Arrowhead. And you say, oh, Molly, it's been done now. But actually, the Molly, I'm not sure it was Molly, but some TMDs is where this has been a breakthrough. It's not in I want to work on this, but they've created like a true Hubbard model simulator. I mean, you know about this, where you have one flat band. So now you just have one interacting, you just have a pair of particles interacting, okay? So, all right. So, okay, by the way, and one nice thing about this field is, it's really real hands-on. So if you're lucky enough to have a colleague like I do, Kuwang, next door, so we all go over there. Everybody comes around, wants to join my group. Even my high school, I have a high school program for this stuff. And, everybody goes over there and we exfoliate the graphene. And you could see and this is what's called the tear and stack. That's how you make the twisted layers. You make one layer of graphene, and you bring this TMD down, and then you pull up and you tear, and then there's literally a little machine, a little thing that just kind of turns it around a little bit. It's very mechanical. And then you put it down again. And this is a really tri-layer system we did. So you can see all these things. These are, not some big fancy accelerator or something you have to do. This is all just sitting there, little stuff. And then this is how you measure all this transport. Anyway, so what is, I'm going to tell you my mathematician's vision, which is always, may not be at all, but I've confirmed it with some very top physicists, and they say, yeah, that's it. Okay. So the idea now is that we all want to study h psi is equal to e psi, right? And the whole thing is, wouldn't it be nice just to be able to play around with any h you want, right? Play around with any h you want, and then you want to study the wave function and explore all the various symmetries and orderings. Okay, just like shape memory materials or all that, it's all the same, really. So how can you do that? Well, because you have all these different options to create your Hamiltonian. There's like 1,000 different possible 2D materials people have gone through with their databases and machine learning, and there's thousands of possible 2D materials. I mean, not all of them may be stable, but and then you could stack them in different orders. And then you can create the different size of the unit cell by varying the twist angle. You can fill up the cells by varying gate voltage. You could even play with inner layer coupling strength by varying pressure, electric field, magnetic field. So when people talk about they talk about this as tuning, right? You tune the system as opposed to just creating a new, cuprate and dope, So here it's very nice. It's just turning a knob now. We're now on turning a knob, and this is, I got a lot of these ideas from a little bit talking to Alan McDonald, and then another guy in this project I'm on, Angel Rubio, and they published a paper, which really is where my kind of vision, of course, comes from, and so here you are. That's what they're doing. They're just sitting there and they're playing all these little 2D materials, and you create little hopping functions, and then you look for these different symmetries and orderings of the wave functions. So yeah, it's a very nice game. It's a nice game, okay? Very fun. And so now if you've got, so that leads to some, you might say, okay, I'm searching for flat bands, and I said there's thousands of materials out there. So we've actually have a little project where we think we can learn the density of states if someone gives me a untwisted material and its local density of states, then we think we can learn the twisted local density of states. Okay, so that's what we're doing, and so we've actually played around with a collection of of like 12 little. And these are little toy models, actually 1D, one linear but still multi-D models, and then we have all different kind of parameters for the hopping functions. And so this is, so along here is our local configuration. This is the energy density for a given local configuration. Now, I keep using this word local configuration. If you have a crystal, then the local configuration of every atom is the same, because it seems the same environment. But on a twisted material, every atom sees a different environment, or if you shift one layer over another. So that's what we mean. But okay, so this is So we have this is like our input untwisted, and then we have a computation of the local density of states in our machine learned prediction. So this is it seems somewhat promising. Of course, we've done a little bit with real materials. I should say my collaborator Stephen Carr has. One could take this big time if there was somebody who really wanted to do it, and maybe it could be how should I put it? It could be a project for exascale computing. Obviously you got to do all these optimizations. This is neural nets. So okay, now as I said, that if you want to I said, okay, we're searching for the flat bands, and I've become fairly expert at that. But then that's for mathematicians, that's like a necessary but not sufficient condition for correlated states. Is that any physicist? Does that sound like some statement a mathematician can safely make, but maybe nobody else? Okay, pardon? Yeah. So in other words, I want to find these flat bands, and but then if I have a flat band, how do I know about all those correlated states? So what that means is you have to really start studying correlated models, or and either by some modeling or computation. Okay, so that means so everybody in this field writes things in this called second quantization form. So this is our single particle model, and this just takes into account electron-electron correlations. And the idea is you want to kind of parameterize. Well, in this case probably it's not so hard, but anyway. But you get a gigantic problem. You get a gigantic problem because if you're really working at the level of individual atoms, then now that's an enormous problem to try to get a band structure or anything from a correlated model. So people are trying. Okay, so there's lots of work, and how can we do some kind of reduced models on this? And this is a very nice idea, which says, okay, I want to instead of just studying the bands, at the level of atoms, let's go and study at the level of the Moiré. Okay, now at the level of the Moiré, I said we had, these colors aren't showing up, but we have some flat bands. So now we can look at wave functions on the Moiré scale, right, for these bands, and I can try to create Varney basis functions for them, right? And that gives me a tight binding model now on a Moiré scale instead of an atomistic scale. So now what people, when they tried to do this, they realized that these Moiré basis functions, they were not as nice as they hoped because they were not so localized. Meaning, so here you have, this is the Varney function centered at this point here. And then you got these like clover leaf. And that has to do with, is the fact that to really have a localized Varney basis functions, you got to have there's some kind of topology constraints you have to satisfy. You need to be able, when you go around the, your Brillouin zone, you don't want to phase. That's the Berry phase and all that business. So there's some, it's even some interesting math still to be done. We've talked about it. And the physicists call this a fragile topology. But in any case, that's a very nice thought, is to just to kind of go and try to do it, do it on the Moiré. Okay, now before I jump into a topic, pretty much all my work has been through the tight binding approximation. Now our tight binding models are not ad hoc tight binding models. They're all kind of fit by DFT, parameterization, Varney basis functions. But some people, I think maybe even Vikram, you think you can do the whole 10,000 atom Moiré cell. Didn't you tell me that?
I mean, depends on how many relaxations we need to do, but if we have a good guess, yes.
Yeah, I mean, actually, one person, I have this Simons Award. I think he thinks he can do it too. I don't know. So again, I can't judge on this, okay? But there are people, that's the thing, is you can be like applied math numerical analyst, and you think you've done something good, and you find out that people can, if they're really willing to go big on computation, they may be able to do the more fundamental problem. So that's all good. Then you still have to go and try to do the correlated problem, which is, again, that's for exascale, right? I suppose. Okay. So I developed this theory with a lot of collaborators. The collaborators' names are like on the bottom of all these various papers. Like I could mention like 20 of them. Maybe I'll just, so my main senior collaborator was Tim Kixeris and Philip Kim at Harvard. And then I had a great grad student and postdoc Paul Cazot, Daniel Massad, grad student. We worked with Eric Kansas, the name goes on and on. Now recently, we at an IPAM workshop, we had a workshop on these 2D materials. And so then I went to lunch with Alan McDonald, and I mentioned, hey, this Simons organization, has these funding for collaborations, and he was quite interested. So we ended up proposing a Simons collaboration, and we actually got something not quite, something slightly different, but it's pretty much the same amount of money. But it's okay. So I have this grant with Alan and Lin, Eric Kansas, Angel Rubio. And also Svetlana Jitimirskaya down at UCSD, who's Maciej Zworsky. Okay, so that's all good. It happened at IPAM, so you never know. Anyway, so I with all my people, we developed this whole theory. I'm just going to give you a taste of it because I'm running out of time already. I started what time? 2:30. 15 more. Okay. So, so meanwhile, I'm developing this whole new theory, not knowing the field much. And it turns out that, of course, other people, such as Alan McDonald, had developed a very beautiful, they call it continuum low energy approach. And this is our approach took insight, but we didn't, I think I kind of lack a certain deeper understanding. But Alan, he kind of had this understanding, and he knew to go right for this low energy kind of continuum model. And so his model is basically, this is it. This is so it's really just a Schrodinger equation, and it's a continuum model. And many of you, and these terms up here are simply these Dirac terms for each layer, and then the T is your Moire periodic potential. So what this says is like, okay, if you're familiar with doing DFT or electronic structure on lattices, crystals, then you're used to your ionic potential being a potential that's periodic on the unit cell, right? So, but here we have a potential. The Moire potential is actually periodic, right, on the Moire scale. So we have a new Schrodinger equation. This equation is, it's actually, hyperbolic. You see, we have these first order terms here. And so this is a dimensionless form of the Bistritzer-McDonald model. And so I got together with my postdoc, Alan Watson, and Alan, and we said, okay, can we prove that this thing really is a valid model? Can we prove it? And so by the way, so the point of view we had is to create a wave packet at this. It's called the Dirac point. That's the low energy point. And so we create a wave packet, and then we see how it evolves, both with the tight binding model compared to, or you could do full quantum, compared to the Bistritzer-McDonald model. Okay, that's the question. Does it really work? Okay, so in fact we have this. I don't have time to do this theorem, but we proved, again, we did all kind of dimensionless stuff. Here's our wave packet, and bottom line is what we proved is luckily for Alan, that in fact it actually, and this is rigorous. It rigorously gives a good estimate at the magic angle for twisted bilayer graphene. Okay, so we got that. That's good. And it also our work shows that if you add these more correlated terms, that our model, this Bistritzer model, is the right model to add extra terms on, okay? So we look at electron correlation, electron phonon, et cetera, et cetera. Okay, so that's in Journal of Mathematical Physics, I guess it is. Okay, so now there's all kind of really fun things you can do with, by the way, now this is just with graphene. We're doing with twisted bilayer. I mean, remember it's a hyperbolic. They call it a Dirac equation. It's like relativity on a different scale, right? It's like relativistic equations now on a plane, different scale, and you can do all kind of. Something you have in relativity called the Klein paradox. Means a wave packet. Wave packet, when you come up against an energy barrier, right? It should. Tunneling means a little bit dribbles through, and the rest gets reflected. Well, in relativistic equations, a wave packet hitting transverse is going to pass through without any reflection. Okay. Plus, you get, and then you could also play games with different energy levels to create like p-n junction, and you can even create little like negative index of refraction And these are all, and so we've actually, with my collaborator, Kawang here, so we've actually been able to realize all these really neat things in, and this was actually just graphene, but we're also doing it in twisted bilayer. So, okay, so now let me just scan through and not do all the theory, but okay, so the main thing is that everything is just, most everything you want to compute is a matter of a trace with respect to some basis of orthonormal basis. And we said, okay, when you put one layer on another at some twist angles, no periodicity anymore. So there's no more block functions and all that business. So we developed a whole new theory based on local configuration, and we do our traces. So we can do all the traces with respect to local configuration instead of over real variables or momentum variables. So this theory, let me just go through here. So we extended it with Christoph contributed a lot to this. We extended this even to things like Kubo formula. Then this is really neat. We've done a lot of work on mechanics. This is some beautiful experiments by Paul McEwen. This is an amazing paper. I can't believe it. This is like your energy landscape of one layer on another. So this just says, okay, AA, see, that's bad. Like I said, you're sitting on top you're sitting there, one layer totally on top of another. Then you go here and you have your like AB, nice, BA, nice, and you go here, and then you go to saddle point. So what these are is, these are, so you have these, this kind of domain structure that I showed you, and I'm doing a lot of work on this recently. So the boundary between the different domains, these are really something called partial dislocations. So they're not quite, full dislocations. And this is what's really neat. In experiments, right? Typically, what you have is a electron diffraction. And so you have these diffraction peaks, and that's really your information. And it turns out to be an interesting problem, and I'll say when you have relaxation. But you can then take your diffraction, zoom in on a little bit around one of the peaks, inverse Fourier transform, right back, and you get this dark field imaging, which is an amazing process. And by choosing your direction, you literally can color, like there's three symmetry-related partial dislocations between and they all come out with different color. This is so amazing. Okay, and here's our continuum model. We've actually just recently been kind of studying as the angle goes to zero, and we have very nice recent paper here. There gives some we actually prove an estimate for domain wall structure, more of a Ginsburg-Landau type analysis. This is then we have another recent work in the mechanics area there's all kind of topological effects. You put one layer on another, and then just because it's not perfect, there's going to be some stretching and things like that. So and these just show the different stretching. This is various kinds of scaling, shear, pure shear, etc. And those all have different kind of topological structure. So we've been analyzing those, and this is coming from experiments of Rebecca Engelke recently at Harvard that we collaborate with. Okay, then probably the thing that maybe I'm really most excited about is we've done, and this is kind of this mathematical idea. I had a bunch of people over at the old IMA, and we still have the space, even though we didn't have the money, and for a year or two. And then I said, so we were some of these young brilliant young postdocs and grad students, and we had developed all this theory for n layers, all general theory. And I said to Ko, can you do trilayer graphing? He said, yeah, I could go do it. So we've been doing that, and now that really, and for trilayer problems, our theory is the theory, because the thing is in a trilayer you have two angles, you have two twist angles, two independent twist angles, and you don't have a 2D periodic structure. It's much more complicated. Again, think of taking a mechanical system and driving it with one frequency, right? Then you'll get a frequency, one frequency comes out. Now drive it with two frequencies that are incommensurate. That's a hard problem, right? And that leads to this what's called mathematical theory of small divisors. But anyway, the problem is that your local configuration is now 4-dimensional, but you're in a 2-dimensional space. So I think so we've kind of got the, so I think this is something that I think we've been able to achieve that really is something as a mathematics, nobody else had been able to do in the physics world. Here's our variational problem, and we have two different driving frequencies. Here's the interesting relaxation. And then let me conclude by something that, so the idea with doing trilayer was to study, correlated effects in another system. Like we thought of this, well, I think we thought of it before all those other platforms came online. You never know. You may be working on something and they're working on it at the same time. And everybody's claiming priority. But we didn't know about, but anyway, this was, so we were doing this trilayer, and then Kurt was actually, as you see, he got experimental results. See here, resistance very low. And the thing about the trilayer system that I really like, it hasn't really been totally accepted in the physics world. We'd probably have Nobel Prizes by now. But so basically, what's called the carrier density is the number of electrons per unit cell, right? That's the important thing. And so when you have a Moire, you have a very small carrier density, because now your unit cell is huge. And now we're talking about 1, 2, 3, 4 electrons. Now when you do trilayer, we call it Moire of Moire. So the size of the unit cell is 1/θ squared instead of 1/θ. Okay. So now so here's my slide I made some time ago. So in the twisted bilayer, the superconducting critical temperature is shown to be 1.7 K. And we got 3.4 K, but their carrier density is on the order of 10 to the 12th electron, right, per cubic centimeter. You put the numbers in. And for us, because we have a Moire of Moire, it's a 1/θ squared instead of a 1/θ, we now have a huge unit cell, much smaller carrier density, and then now what's called the Fermi temperature scales like the carrier density to the square root. And as I started off saying, all these, what's really interesting from the basic science point of view, right, is a scaled variable, right? So maybe for technology, you want high temperature superconductivity, but from a theoretical point of view, you want some kind of scaled. This is what enters into your theory, is some scaled parameter, and that's Tc divided by Tf. I haven't verified all that, but that's what I believe is the case. So for that, with our very low carrier density, that would give this material the highest scaled critical temperature for superconductivity. So Anyway, so actually more and more people are getting interested in this. Our paper took a while to get through the system, but it did get what they call it, editor's choice and PRL in the end. So anyway. So anyway, let me see. I guess I'm probably running out of time and voice. So I think I'll quit here. Thank you.